Alright team, so here's the review for the test tomorrow. Hope this will help out. Sorry it's taking so long to get it up, but we had a bunch of kids after school making their mousetrap cars, so you should too. A mass of, let's get my marker here, 80 kilograms, runs up 3 flights of stairs in 12 seconds. The student has gone a vertical distance of 8 meters. Determine the amount of work done by the student to elevate the body to this height. Assume the speed is constant, which really doesn't matter. So remember that work equals force times distance, cosine theta. But if you remember, well, if you think about the potential energy lab that we did running up the stairs, so if they're both up, cosine theta is actually cosine of 0, which means cosine of theta is 1, which means nothing. Remember FD, it's just how much force to get themselves up those stairs. And you guys did it. The force is actually from gravity, so the student's weight times the displacement, which was 8 meters. So if we know that the student's mass is 80 kilograms, uh, 8 times 80 times 10 should be 6,400 joules. And get rid of that. I mean, this is exactly what you guys did during the power lab. The fact that they go in 12 seconds doesn't mean anything because we are not asking you anything about power. We are only asking you about the work. Okay? So they have to do work on themselves to lift themselves up. Number 2, when doing a chin-up, a physics student lifts her 42 kilogram body a distance of a quarter meter in 2 seconds. What's the power? So now we have to do, all right, power equals work over time, but we don't know what work is, and work equals FD cosine, cosine theta. But again, she's lifting up, so the force is up, the displacement is up. So both of those are going to give us cosine of 0, and cosine of 0 on your calculator is 1, so it's FD times 1. So what that turns into is work equals the force, which is 42 times gravity, which is 10, times the displacement, 0.25. So 42 times 10 times 0.25, we end up with a work of 105 joules. But we're not asking for work, we're asking for power. And that is power equals work over time, which is 105 over 2 seconds, which equals 52.5 watts. Okay? And again, up means positive work, and you know, if she was pulling up but going down, that would be negative work, and that's kind of important to remember tomorrow. So just remember, positive work is when the force and the displacement are in the same direction, and negative work happens when force and displacement are in opposite directions. Determine the kinetic energy of a 625 kilogram roller coaster that's moving at a speed of 18.3 meters per second. This is easy. Kinetic energy equals 1/2 mv squared, which equals 1/2, the mass is 625 kigs, times v, which is 18.3 squared. So 0.5 times 625 times 18.3 squared. And that would be a whole bunch of joules. 104,653.125 joules to be exact. And I hope that that makes a lot of sense because it's just simply a plug and chug problem. Next, a student drops a golf ball from a height of 2 meters. The ball has a mass of 0.04 kigs. What's the speed of the ball as it reaches the ground? So this is going to go back to conservation of energy. PE plus KE equals PE plus KE. How do I know to do this? Because I've got a set of initial conditions and then I've got a final condition. So my potential energy is what my ball and I've got no kinetic energy because I'm holding it, equals PE at the ground is going to be 0 plus KE, which is 1/2 mv squared. Now we can start plugging some stuff in. The beauty is the masses cancel, so I don't even need to give you that 0.04 kigs. So G is 10, and the original height is 2, and that's going to equal 1/2 v squared. So 20 equals 1/2 v squared, and I got to multiply both sides by 2 to get rid of that 1/2. So 2 times 20 is 40, and that equals v squared. So square root of 40 equals 6.32 meters per second. E equals 6.32 meters per second. I hope that helps. Next, meters, the pile driver is opposed by 5 times 10 to the 6, that's 10 to the 6 newtons. I can't type that. How far is the stake driven? So we're asking for a displacement. This is actually a really tricky problem, but if you think about it, it's really not that hard. We're dropping this 3,000 kilogram mass for a distance. So there is, right, and which is mgh, and that gets turned into work, which is FD. Okay, force times distance cosine theta. And what's happening is the pile driver is going up. If you don't know what a pile driver is, it's a big old cylinder, and it moves up and down. Let's see if I can do this. It goes up and down, and it basically hammers something else into the ground. So let's say you got that fence pole. The pile driver goes up, it's a big hammer, and drops on the pile driver, or drops on the fence stake, and the fence post drops. So they're telling us how hard the fence post is forced down, because it's resisting with 5 times 10 to the 6 newtons, which means it's encountering 5 times 10 to the 6 newtons. But you know, this is a kind of a complicated problem, but the theory is you do potential energy, you give potential energy to this pile driver, it does work FD cosine theta on the stake going into the ground. So if we know how much potential energy we have, we know how much work can be done on the stake. So the mgh actually equals cosine theta. But if you remember, the stake is going down, the force is going down because that's the force on the pile driver, and we actually know how big that is, which is 5 times 10 to the 6 newtons. And they're both going down, which means theta is 0, which means FD cosine theta is FD times 1, because cosine theta is cosine 0, which is 1. So the m is 3, g is 10, the height is 10, and that equals the force, which is 5 times 10 to the 6 newtons, times the displacement. So there's the start of the problem, at least. Now we can start doing some calculations. 3,000 times, not 300, 3,000, 10 equals 300,000. I don't know why I did that on my calculator. Equals 5 times 10 to the 6th. 300,000 divided by 5 10 to the 6th. So 5 times 10 to the 6th d. Then we divide both sides by 5 times 10 to the 6th. 5 times 10 to the 6th. My handwriting is terrible when I'm trying to rush, but I want to get this out to you before 6, because that's what I promised. 10 to the 6th. So these will cancel, and your displacement actually ends up being 0.06 meters, which is 6 centimeters. So This might be a little more esoteric than what's going to be on tomorrow's quiz, but I think you're loading something up with potential energy, and it ends up doing work on an object. So that's really what I'm hoping you'll understand. Next up, a Six Flags New England Agawam, Massachusetts ride called the Cyclone. It's one of the best roller coasters there is. Ascends a 34.1 meter hill and then drops 22.9 meters before ascending the next hill. Train of cars has a mass of 4,000 kilograms. First off, how much work is required to get the empty cars to the top of the first hill? Well, first off, the work, just like you guys running up the stairs, is going to be mgh. So the work to get to the top of the first hill is going to be 4,000 times 34.1 meters. So 4,000 times 10 times 34.1 is going to give us a lot of joules. 136,423 joules. So this is the potential energy or the work done getting to the top of the first hill. And if we know anything about the conservation of energy, this is the amount of joules that you have for the whole ride. Okay? So the second piece, what power must be generated to bring the train to the top of the first hill in 29 seconds? So now we can take this, so that's letter A. Letter B, well, what do we have to do this in 29 seconds? We can take that and divide it by 29 seconds. 13,64000 because power equals work over time. So that's that. And we end up with 47,034 watts. Okay? So I hope a little bit. Let's try and get my handwriting a little better. 47034 watts. And then for letter C, converted into kinetic energy from the top of the first hill to the bottom of that 29 meter drop. So now we have a couple of little nuances here. We remember PE, this is an initial situation, so the car's going up and then it drops almost 22 meters. So PE plus KE again equals plus KE. And at the top we know our PE, and that's 1,364,000 joules. But there's no kinetic energy at the top there, so it's barely moving. I mean, it's essentially negligible. And that's going to equal the PE at the second hill. Now the problem is I'm kind of being a little tricky here. First off, then drops 22.9 meters between ascending to the next hill. So I should probably have made up my mind. Do I want it to be 21.9 meters or 22.9 meters? A little typo in there. So I am sorry. Top of the hill to the bottom of the 22.9 meter drop. So it drops 22.9 meters. So if we start at 34.1 meters and we drop 22.9 meters, that means we still have 11.2 meters of height, which means we still have potential energy at the bottom of that drop of M, 4,000, times G, 10, times H, which is 11.2 meters, plus our KE. So I want to know how much P is converted into KE? We got to solve for the KE. So 1364000 equals 4,000. I'm going to do this on my calculator. Times 10 times 11.2. 448,000 joules. Plus KE. So how do we solve for KE? 1364000 minus 448000. We should end up with a, oops, didn't mean to do that. We should end up with a kinetic energy of 916,000 joules. And then D asks us, well, how fast is that? Well, we know KE is 1/2 mv squared. 916,000 equals 1/2 mv squared, but we know the m. So 1/2 times 4,000 v squared is 916,000. Let's see, what can we do? Half of 4,000 is 2,000. 916,000 equals 2,000. Divided by 2,000. That's going to be 458 equals v squared. So divide both sides by 2,000. Divide both sides by 2,000 equals v squared equals 458. And then I have to take the square root of both of those. And I will end up with a velocity of 21.4 meters per second. So it's a little less than 50 miles an hour at the bottom. So I hope that helped. It's pretty straightforward. Figure out the potential energy, find out the power, use conservation of energy to figure out how much potential becomes kinetic, and then how fast does that kinetic actually represent that you're going. Coyote, his mass is 15 kilograms, chasing the road runner when the coyote runs off a cliff and plummets to the ground 40 meters below. What force does the ground exert on the coyote when he makes his dent 0.6 meters into the ground? This is just like the actual pile driver problem, where your potential energy turns into work, and that is force distance cosine theta. But a force up, and the coyote is landing down. So we're going to be a little interesting. But in any case, the potential energy is mgh. So the mass is 15 kilograms times 10 times the height, which is 40 meters, equals 4 times the displacement, 0.6, times cosine of 180 this time, because the ground is forcing coyote up, but the coyote goes down, so there's 180 degrees between that. So 15 is 40. That equals 6,000, which equals F times 0.6 cosine 180, and that's going to be negative 0.6. So 0.6 times cosine 180 is negative 1 times 0.6. That's why it's negative 0.6. So then we got to divide both sides by negative 0.6. 6,000 divided by negative 0.6. A force of negative 10,000 newtons. So he's going down. We are talking about a negative force, which is a force pointing up of negative 10,000 newtons. What force of the ground? I mean, you can. I'll forgive you if you don't have the negative there. But basically, he's going down. The force is pushing him up, so it's opposite of his displacement, which is there you go, because it's negative work. Bella. Let's see, how much more do we have? 2 more. All right, 2 more. Bella, a cat whose mass is 4.8 kg, is napping on the refrigerator when she rolls over and falls. She has a kinetic energy of 100.6 joules just before it lands. How tall is the refrigerator? So this, she was asleep and now she's on the floor. So we again have an initial condition and a final condition. I would say use the law of kinetic conservation of energy. Potential energy, mgh, plus kinetic energy. Kinetic energy, which is 1/2 mv squared, equals potential energy plus kinetic energy, which equals, again, potential energy plus kinetic energy. So what do we got? The cat is, so she falls and has a kinetic energy of 100.6 joules just before she lands on the floor. So we know this is going to be 100.6, and we also know she's landing on her floor, so the MGH, the height's probably 0 if she's landing on the floor, so there's no potential energy there. Okay, so that means total energy at the end is 100.6. Well, when a cat's asleep, they're not really moving, so the initial condition is also going to be a kinetic energy of 0. So the MGH must be 100.6 joules. Okay, so that's a J. So the potential energy and the kinetic energy essentially are the same, and that equals 100.6 joules, and we know the cat's mass is 4.8 kigs. We know gravity is 10. We can figure out the H. If I can make an H, which equals 100.6 joules. So 4.8 times 10. Why did I do that on my calculator? That's 48. 48H equals 100.6 joules. Divide both sides. Now I'm going to need my calculator. 100.6 divided by 48 should give us an H of 2.095 meters. Next, from a height of 2.15 meters above the floor of the Boston Garden, Paul Pierce shoots a ball straight up next to the hoop with a velocity of 4.2 meters per second. If his basketball has a mass of 0.6 kilograms, will his shot go as high as a 3.04 meter hoop? Use the law of conservation of energy. So we have initial conditions and final conditions. PE plus KE equals PE plus KE. MGH plus 1/2 mv squared equals MGH plus 1/2 mv squared. So to start with, the height is 2.15 meters and the basketball is 0.6 kilograms. So 0.6 times 10 times 2.15 plus 1/2 times 0.6 times the velocity that he throws it with, 4.246 meters per second, equals MGH 3.04 times 10 times the mass, which is 0.6. Sorry, that's H and that's M, but I just got it backwards. Plus kinetic energy. Now, I guess the question is, what's the worst case scenario? He's going to throw it up, and the worst thing that happens is the ball is going to stop. You know, maybe he throws it up hard enough and the ball will keep going, but I guess the real question is, how much potential energy do we need here, and how much energy do we have here? And will they equal each other, or will one be bigger than the other? So if we can assume the worst case scenario, that the ball stops, and this is all the energy that the ball has, we can sort of try and figure this out. And the question really is, look, the ball has this much potential energy, the ball has this much kinetic energy. Does the ball have enough on this side of the equation to reach the top of the hoop? So it's not even equals, it's more like equals question mark. Is there enough energy on this side to get the ball to this much energy on this side? And then you just kind of plug it in. It's not even like you're solving for something. You're looking at the initial energy before and the final energy after. So 0.6 times 10 times 2.15, that is 12.9 joules. And 0.5 times 0.6 times 4.246, that is 1.2738. 1.2738 joules. And total, that is 14.17 joules. So Paul Pierce gives the ball 14.17 joules. If it's going to get that high, it needs at least 14.17 joules. So let's see, 3.04 times 10 times 0.6, that is 18.24 joules. So in order for the ball to get this high, it needs 18.24 joules. Paul Pierce only gave it 14.17 joules. So you don't have enough energy on this side. Well, you don't have enough energy from Paul Pierce in the beginning to get the ball to go 3.04 meters up. So the answer is no, not enough energy. And for what it's worth, you can ask, well, what could he do to make it better? Maybe he throws it faster. So instead of 4.26, maybe he throws it with 6.26 or 6.246 meters per second of velocity, which would make this side bigger. This side might, this side won't change because this is where the basketball hoop is, but giving more energy at the beginning might give you a better shot of having it actually get to the basketball hoop. So I think that's it. Everything else on the test is pretty straightforward. I'd really look at your notes on positive versus negative work. I'd know your equations. Work equals FD cosine theta. Work also equals the change. Do this right. Work equals change in kinetic energy. Net worth, and that's what net work is. W net. And then we started talking about types of energy. PE, mgh. KE is 1/2 mv squared. Power is watts, which is work over time. And then I don't think I'm going to have you do any horsepower stuff, but if you really need it, 1 horsepower equals 746 watts. All right, so I hope that that about does it. That's the equations you need to do. I hope you were conscious during class and you can answer some questions about this stuff. Good luck studying.